So we're going to continue looking at Anova methods. Now, the Anova methods that we're going to be discussing in this subsection deal with an experimental design called a randomized complete block design, or RCB for short. Our goal is going to be to compare two or more population means again, but the way the sample is taken is in such a way that that observations are dependent, or at least some observations are dependent. This is going to be very similar to what we saw before when we were looking at a hypothesis test or confidence interval for mu sub d. If you remember, mu sub d actually meant that we were talking about the difference between two different means, but the d there was for difference, that we had these observations that were taken from two different populations and they were paired in some manner, and so we adjusted our data so that we just looked at the differences. Now with RCBs, again, our data is going to be, let's say, grouped, or in the terminology here with RCBs, going to be blocked in some manner. So we're going to have a number of observations that always have something in common. So for example, back when we were doing inferences for mu sub d, we were interested in an example dealing with which grocery store has the lowest prices on average. And the way to go about doing that is to sample the same items at two different stores. Like maybe, for example, you get a Wheaties box at Walmart, you get a Wheaties box at Hy-Vee, look at the two prices. Then maybe you go to some other item, such as a particular type of flour. So you sample the exact same flour at Walmart and also at Hy-Vee, get the prices. Now we're going to be extended to a situation where maybe we had a third or fourth grocery store, and once again we sample the items. We sample the same items at each store, and so essentially, if we had, let's say, 4 different grocery stores, then we're going to be sampling items, let's say, by a group or a block. So maybe we get Wheaties at Walmart, Hy-Vee, Super Saver, and another grocery store. Now, by doing that, then, what that's going to allow us to do is account for a source of variability that we were not able to necessarily account for with a completely randomized design. And for this reason, then, what's going to happen is our SSE now is going to be smaller once we account for this thing that we call a block. And I'd like you to think about it on your own, why having a smaller SSE would be important. Think of it in terms of power. Think of it in terms of the width of a confidence interval. And if you have questions about why it would be important to have a smaller SSE, please ask. Okay, so let's take a look at some other examples where a randomized complete block design could be used. So for example, we talked about wheat varieties in the past, and which wheat variety or results in the highest yield. And so we have these particular wheat varieties here, 7 in total. And what we could do is, let's say, find one location in southwest Nebraska. So maybe we want to make inferences to all of southwest Nebraska. And here, for one particular location, one farm, so you obviously see from my image that it must be a farm, we have 7 different plots where we plot one variety in each of the plots. Okay. Then we find some other locations in southwest Nebraska as well. Maybe location number 7 looks something like this. And again, it must be a farm given my graphic there. And we have these 7 different plots, each with a different wheat variety on it. Here in our particular case then, our data would eventually look something like this, where I have the little y's there as a symbolic representation of what the actual numerical values would be observed. Here in this particular case, we're essentially grouping, or the term that we typically use more often, we are observing our data in blocks. So the first block is location number 1. The second block is location number 2. And since these are being sampled at these different blocks, within a block, you would expect to have some some similarities, maybe because of weather conditions during the growing season were maybe at location 1, where maybe it was different for them from location number 2 or from location number 3, even though they might be all in southwest Nebraska. So the yields that we get, denoted by the Y's there, might have some similarities to them by location. And we can take advantage of that, this similarity, in our analysis that will then lead to a smaller SSE than if we wouldn't have taken that into account otherwise. Okay, so with respect to our previous terminology, our response variable is the yield. Our factor is wheat variety. We have 7 different factor levels, or 7 different treatments. Our experimental unit is going to be a plot of land at a particular location, and our block is going to be location. Now, ideally, what you would like to do is randomly select maybe particular farms to participate in this experiment in southwest Nebraska. What that will allow you to do then is to generalize your inferences perhaps to all of southwest Nebraska. What might actually happen in actuality is the farms couldn't be necessarily randomly selected, but what you're hoping is to get a nice, let's say, geographical sampling. Okay. So the second example is one that we're going to come back to. We're going to focus on for the rest of this set of notes, and deals with golf balls. And so what golfers really want to know is, well, what type of golf ball travels the farthest, let's say on average, when struck by a driver? So we have 4 different golf balls, and I just so happen to have the first kind of golf ball there, a max fly. And what we like to be able to do amongst these 4 different kinds of golf balls is determine, well, which one's going to fly the farthest on average. That's the kind of golf ball that I would want to play with, and most other golfers would want to play with. Although I will admit there are other factors that would be of interest to golfers. So it's not just distance, but distance is a huge one. Okay, and so a few years ago, I was looking at a website on golf balls, trying to decide what kinds of golf balls I should choose for myself, and I came across this website. It was for the manufacturer of Top Flight, and they say using a driver, Top Flight will be the longest of all the golf ball types. Where a particular type of Titleist golf ball, let's say type B, is -3 yards, or it's let's put it this way, 3 yards less. Titleist P, 6 yards less. Max Fly is 4 yards less. Now, I would assume, based upon the way that this information was displayed, they're probably talking about the average length. Because, of course, not every time that you hit a golf ball is Top Flight always going to be 3 yards longer than Titleist B. Obviously, there's a number of factors that affect the distance. It could be where exactly. So I got my golf equipment out just for this particular video here. Where exactly are you hitting the golf ball on the driver? If you're hitting it here sometimes, if you're hitting it here, or if you're hitting here. Now, obviously, or if you're a golfer, you always want to hit it right here, but it's hard to get it there every single time, and I especially know that myself. But anyway, oops, there went my driver. Anyway, there's going to be variability from every time that you hit the golf ball. It could also be due to weather too, like wind speed. So I would imagine what this website was talking about was on average what the distance would be. And unfortunately, this website didn't actually provide any data to support their claim. And they didn't give an explanation of how they came up with this information. How did they perform an experiment? So when I saw that, and given that I'm a statistician, I thought, well, wait a second. Well, how would I go about actually performing the experiment in this particular situation? So what I decided to do was think about that, and I actually ended up simulating some data corresponding to how I would actually approach the experiment. The simulated data, obviously, since it's simulated, could come up with different conclusions than what Top Flight had. So this isn't real actual hit data. But here's how I would go about doing the experiment. And let's say I didn't have access to any kind of like a robotic machine that could hit the ball for me. And so what I would do is go out and select, let's say, 20 amateur golf balls, 20 amateur golfers of varying abilities. And they're going to be, let's say, essentially randomly sampled from the population of all amateur golfers. Now, obviously, that might be difficult to do. And so you're going to have to make assumptions that, let's say if in where I live in my city, maybe I select 20 golfers from there. And what I have to assume is that the amateur golfers in my city are representative of every other city as well. And so each golfer used their own driver to strike each type of golf ball in a random order. So maybe one time they hit a max fly, the next time they went ahead and hit a Titleist. Let's say maybe this is Titleist P. Actually, it is Titleist P. Maybe the next time they hit Titleist B, then the next time they hit Top Flight. Then the next golfer maybe steps up, and this time they hit Titleist P, and then they hit Max Fly, and so on. You want to randomly order them because you don't want any kind of bias to come into play. Because if, let's say, everyone hit Max Fly first and then Titleist B second, there we go, there's Titleist P. A golfer from hitting that max fly might learn, oh, I'm not hitting my swing correctly, so I'm going to adjust then on my second hit and hit that one better. So, okay. And what would have been done in this experiment, the distance each ball traveled, the carry distance, though it does not include each ball traveled in the air, that is, not including the roll, is recorded in yards. The experiment was conducted under ideal golfing conditions. And here's what could have happened in terms of the ordering for the golfers, how they hit the golf balls. Now, on your own, you should think about what function in R could we use to actually construct a table such as this that would randomly select the golf balls and then give them to a particular golfer in terms of the type to hit in order. Let's say, again, this is all simulated, and also these are all amateur golfers, so you're not going to hit drivers necessarily over 300 yards. Here's, let's say, the actual data that was observed. So golfer number one, for Titleist B, they hit it at 190 yards. Excuse me. Max fly, 211 yards. Titleist P, 203 yards. And top flight, 205 yards. Okay, not necessarily in this order. It's just this is the way that this is being summarized in the table. So let's look at our previous terminology then. Our response variable is going to be the distance. We're going to measure the distance that the golf balls travel in the air. Our factor of interest is golf ball type, one of the four. Factor levels are the four different golf ball types, as are the treatments. Our experimental unit is going to be a golf ball. And a blocker in the block is golfer. So notice how all four of these for golfer number one are connected in some way by the same golfer. All four of these for golfer number three are connected in some way by the golfer. And you can imagine that each of these golfers have varying abilities. And what we like to be able to do is account for that variation in their abilities in our analysis and essentially take it out, that variability, so that now that my SSE is going to end up being smaller. Okay, so we are on page 7. Okay, next let's look at the R aspects of this golf ball example. So I have my data. Let me go over here to 10. My data is in golfballs.csv. I'm going to read it in to R. And there you can see my data, which was partially displayed in that table. Now, what I'm going to need to do is actually reshape, or I shouldn't say necessarily reshape, but reconfigure my data so that I can actually end up doing some plots with it. And what I would like to do, let me actually show you the final result. So again, here's our data where each row represents the results from a particular person. What I'd like to do is reconfigure the data so that now I have each person represented by a row again. I have their corresponding golf ball type and the distance that they hit it. And so, in other words, I'm basically going to take, this might have been an easier way to explain this. I'm going to take this portion of my data here. Let me actually remove my break here. And take that portion of my data. And then what I'm going to do, I'm going to take my max fly. I'm going to put it right below where Titleist B is, and then I'm going to repeat the numbering 1, 2, 3 down to 20 for the golfers. I'm going to do then the same thing for Titleist. I'm going to take that now below where max fly is. And I'm going to do the same thing for top flight. Take that below where Titleist P is. And again, the reason for this is I want to do some plots. In order to do the plots correctly, I need to reconfigure how my data looks. So now to do this, let's copy and paste some of this outside of it first so that we can see how this all works. Okay, so what I'm going to do is I'm going to grab from my GB data frame each of the people. I'm going to create a new variable called Titleist B. And the way that R is going to react is going to put every person having a Titleist B as their type. And then I'm going to also grab all the distances for the corresponding Titleist B. So let's go ahead and do that. And so even though there was only one value here, Titleist B, there's 20 values here for person, 20 values for Titleist B, the way that R reacts, it actually replicates Titleist B 20 times so that everything has the same length. And so there's one particular data frame. And we can do the exact same thing with max fly, person, the type of golf ball, the actual distance that that particular golf ball flew. And there's those values. So what I want to do is take this and put it right below the Titleist B values. And how I can do that is to use a function called rbind in R. Oops. Rbind stands for combined by row. And so when I do that, notice how everything is now as I had wanted. All the Titleist B values and then all the max fly values. When I use the rbind function, notice I put a comma between specifying the two data frames. So now I'm going to repeat the same process for the other two types of golf balls, and we'll look at the head and the tail of the resulting new GB2 data frame. And you can see that indeed I have my Titleist B's first, I have my Titleist P's last. Notice that there are a total of 80 observations there because we had 20 golfers for each of the types of golf balls. There are other ways that one could have reshaped or reconfigured the data frame, other functions that could have been used for this purpose too. You're welcome to take a look at how you use a function called stack to do it. Another way is to use the reshape function as well. Okay, so now with that particular form of my data, let me jump back over here to Word. I want to do some plots. Okay, so what I'm going to do is my usual box and dot plots. So I have my distance on my y-axis, I have golf ball type on the x-axis, and what do we see here in comparison to what we've seen in the past when we've done this? Well, what we typically look for is sort of like a shift in the points from, let's say, one of the factor levels to another. And what we see here is a lot of overlap between the observations across the factor levels. Sure, the median is higher for max fly in comparison to the other ones, but I look at how this is overlapping this right there. And so you might be thinking, uh-oh, we're really not going to based upon what we see here, we're probably not going to be able to find differences amongst the population means for these particular golf ball types in terms of the distance that they actually fly. However, we're not looking at the data in the right way because we have a lot of variation from one golfer to the next. And that's actually what's causing a problem here in us being able to view this data. What we like to be able to do is take that variation out and then redo this exact same plot. Okay. So the key is that we're not taking into account block when we're looking at the data like that. And so that previous plot is how we would have approached it if we had a completely randomized design. So to take into account then the block and the golfer abilities, you could say, what we're going to do is use the aggregate function as we've done many times before, where I'm going to aggregate by distance. I'm going to aggregate distance by person. And how am I going to aggregate it? Using the mean. So if I go ahead and run that code, I put the results into distanceblock.adj. Maybe I should call it distance block mean. What we have here is that the mean value for person 1 was 202 yards. The mean value for person number 2 was 166.75 yards. And this is again across the different golf ball types. Using then this information, what I'm going to do is try to merge all these, or how about this? I say it this way. What I'm going to do is take my original data, and what I like to be able to do is put all the block means, all the golfer means, right next to the corresponding golfer values. So in other words, let me run this code, then I'll come back and explain it. Okay, so for person 1, they actually have 4 different observations: titles B, titles P, max fly, and top flight. Here are their corresponding distances. And then what I did was I merged into this data frame what their corresponding overall mean was. So the overall mean of 190, 203, 211, 205 is 202.25. Then if we look at the very last person, again, we have the 4 different golf ball types. We have their corresponding distances for each golf ball. And then the overall mean was about 177 yards for that golfer across the different types. And how did I do that? I use a function called merge. So what I'm going to take is this GB2 data frame. This was again the reconfigured data. And I'm going to try to put into that data frame, or merge it, I should say, with another data frame that has all the means by golfer. How do I want to merge them? By the person. Because notice that distance.block.adj has the person number in there. Also, if I come back up here, GB2 also has the person number in there, so I want to merge by person number. So for my X argument, I want to merge by person. For my Y argument, I want to merge by person. And then I'm just going to make it pretty in the end how I label some stuff. You can look what happens when you don't include the suffixes argument on your own. And so when I run this then with GB3 and looking at the head of it, and I guess we've already seen this before, now I have mean by person, so 202.25, 202.25 in the correct parts of this new data frame called GB3. If you end up having any questions about that, let me know. Merging 2 data frames is a very common thing that we do in statistics to get a data set in the format that we want. So it's important that you do understand what merging is and how to do it. Okay, so now what I like to do is I like to adjust each of these distances by the overall mean for the particular person who's hitting the golf ball. In essence, what this is going to do is allow me essentially to take golfer ability out of our plots that we're going to eventually look at. So I'm going to create a new variable called distance.adj for adjustment. I'm going to put that into GB3, and it's going to be the distance minus the actual average distance by person. So if I do that, there we go. So if we take 190 minus 202.25, we get negative 12.25. This adjusted distance is now what I'm going to plot. So I do my box and dot plots again. Of course, I open up in the wrong screen. There we go. Actually, let me look at it in Word so I can draw on it really easily. Okay, here's my plot now. So on the y-axis is these distances that have been adjusted by golfer. Okay, the x-axis is the golf ball type. Now, in comparison to when we've looked at these plots before, again, what we do is we look for shifted points from one factor level to the next. And take a look at this. MaxFly. MaxFly seems to be adjusted or shifted upward in comparison to definitely Titleist B, and to some respect even Titleist P and Top Flight overall. So when we see this shifting there, again, that's going to tell us that, something's up here. Maybe for the population itself, MaxFly might have the greatest mean average distance in comparison to the other three golf balls. Maybe. Again, this is just a sample. And what we're hoping is that this sample is going to give us enough information that we can conclude for the entire population that this same thing holds. Okay. So similar to what we saw with completely randomized designs, we have an Anova table that helps to summarize the various calculations that we're going to do. So for example, I shouldn't say necessarily for example, here it is. So we have the source of variation like we did before. And in fact, all of the column tiles are exactly the same as what we've had before. We have treatments. And with treatments, we're going to have a sum of squares for treatment. We're also going to have a source of variation called error. And corresponding to error, once again, we're going to have sum of squared errors. And then in the last row, we have a total, which is going to be the sum of all the sums of squares. Okay. But now we have a new element to our table called blocks. And basically what we're doing is this is another partition of the overall variability, this TSS. Another partition of it that talks about what's the variation that's contributed to the experiment from these blocks. With the sums of squares, we have corresponding degrees of freedom as well. So treatment, just like before, is number of treatments minus 1. Blocks is going to be the number of blocks minus 1. Error is going to be a little bit different now. T minus 1 times the quantity B minus 1. Then if we take these sums of squares, divide by the degrees of freedom, we're going to get mean squares. And in the last column, we're going to have our F test statistics. And in particular, we're going to be very interested in this one right here. Mean square for treatment divided by MSE, mean square for error. This is going to tell us if we have a difference amongst the population means. Okay, so in terms of all the stuff that's in the table here, I've actually written out what the actual formulas are. You can take a look at these formulas on your own. They're very similar to what we had before, but there are some differences. So sums of squares for treatment. Remember how we found this before. We took the mean for the treatment or the factor level, and we subtract off the overall mean. We squared, we added across all the treatments, and then we weight by the number of observations that were for a particular treatment. Here in this particular case, the number of observations ends up being B, which is the number of blocks. Before, with a completely randomized design, instead we had N sub I. Okay. Now for sums of squares for block, look at this. So y bar dot j, what this corresponds to is the mean for a particular block. So for example, y bar dot 1 for the golf ball example would be the mean distance for golfer number 1. We then subtract off the overall mean for all the observations, square it, add it up across all the blocks, and then we weight by the number of treatments that we have. This is the number of observations per block. Okay. Now, one can show actually through algebra, one could show that the total sums of squares is equal to the sums of squares for block plus the sum of squares for treatment plus the sum of square for error. Now, if we wouldn't have taken into account the block, and if we would have analyzed this as a regular old completely randomized design, our SSE would have been the SSE from this RCB and the SSB from the RCB. Those two would have been added together. So from this, you can see that definitely SSE is going to be smaller than what it would have been with a completely randomized design. Okay. Now, when the treatment means, the factor level means, the population means are equal to one another, one can show that the expected values of the random variable versions of MSC and MST are equal to sigma squared epsilon again, just like what we had with completely randomized design. Also, like with a completely randomized design, when the equality of the means is not true, the expected value of the random variable version of MSC is still sigma squared epsilon. But now the expected value of the random variable version of MST is now higher. And so because of that, then, one will want to look at the ratio MST divided by MSC. The larger this ratio is, the more evidence against the null hypothesis of equality of means, just like what we had with a completely randomized design. Also, if we think of MST divided by MSC, that quantity is a random variable. It actually has an F distribution if the null hypothesis is true. So we can find corresponding probabilities with this term, just like what we've done in the past. We can then, as you can imagine, find p-values as well. Excuse me. And, we need to decide, well, how large does F obs have to be in order to reject HO? And so we look at the extreme portion of our F distribution. How do we define extreme? That's where a critical value comes into play. Okay, so let's take a look at this more formally with the test statistic method. Step 1, we state our hypotheses. Step 2, our test statistic, MST divided by MSC. Step 3, state your critical value. Please take a look at the corresponding degrees of freedom. Step 4, if F obs is greater than the critical value, reject. Otherwise, don't reject. Step 5, what does this mean in terms of the original problem itself? Page 16 here, we have then a template of how to make the actual wording. Again, with this template, make sure you put it in the context of the actual problem itself. So then with the p-value method, how do you calculate the p-value? Suppose you have a random variable x that has an F distribution with the appropriate degrees of freedom. You look at what's the probability that x is greater than F obs. P-value small, reject. Okay, so let's get into this golf ball example once again. How can we get this Anova table? Well, as you might expect, we use the AOV function, just like what we did before. We have a formula argument. Our response variable, in other words, y sub ij, is our distance. And we say tilde. And it doesn't matter which order you put these in, but you need to pay attention to what the order is. Then when you look at the corresponding Anova table, here I have type, which will be the corresponding golf ball type, plus then the actual person. So in the data frame itself, if you notice, we have person 1, person 2, and so on. So it's a numerical quantity. And we need to tell R that that, let's say, person 2 is not greater than person 1, or person 20 is not greater than person 10, just because of the numerical way that we're labeling everything. And so to do that, similar to what we had with the Wheaties example, we say factor parentheses person in parentheses. My data is in GB2. I should have mentioned too that we are not working with the distance adjusted data here. We can work with the data itself without that adjustment. We will come back to the adjusted data later. The primary reason why we had the adjusted data was so that we could see things graphically in our plots. Then when I say summary of the resulting object mod.fit, here is essentially my Anova table that we had before. So for example, here is SSE, here is MSE, and let's see, so this, oops, that's not, excuse me, I mislabeled that, excuse me. Let me try that again. Here is SSE, here's MSE, here's SST, MST, and this F, 6.36, comes from taking 596.9 divided by 93.8. Okay, get 6.36. The corresponding p-value is 0.000853. So it looks like we do have a lot of evidence here that indeed the mean golf ball, or the mean distances that these golf balls go, are different based upon the golf ball type. So if we formally then do the test then, using alpha 0.05, so I set up my hypotheses like this, where in the subscript here for mu, I put a descriptive label to tell what we're talking about, which kind of golf ball. Here's my test statistic of 6.36. My critical value, I can find that once again using the QF function. I get 2.77. So test statistic is greater than the critical value, reject HO. What does this mean in terms of the original problem? Well, there is at least one pair of golf ball types that have differences in their mean distances. How do we find the p-value? Well, we take our test statistic, we put it into this probability statement, use the PF function, and that's how you would find the p-value, or you could go back to simply the p-value that's listed already in our output. Okay, so what are the consequences then of rejecting HO here? Well, this means that some golf ball types are better on average with respect to distance. This may lead golfers to prefer one type of golf ball to another. And as I said before, there are other factors to consider too, but distance is often a huge factor in how a golfer chooses a particular kind of golf ball. Okay, now what would happen though if we did actually analyze the data as if it were a completely randomized design? So I can use exactly the same code as above, but now I don't put person in there. I just put type in my formula argument. I save the results into mod.fit.crd, and here is then my corresponding Anova table for a CRD. Look at my F value. Look at that p-value there. It's quite high, 0.67. And to be honest, it's really not surprising given, if I go back in the notes here, that is not surprising at all given what we had seen in this plot. You know, we saw this large overlap from one golf ball type to another. P-value 0.67, yeah, that seems reasonable based upon what I see there. So that's not surprising. And again, the reason why that occurs is because there's a lot of variation amongst the golfers. And once we take that out of SSE, our SSE really drops. And because SSE then is in the denominator of FOBS, our FOBS goes up. So in particular, if you go back to our output for the RCB, find SSE, find SSB, look at how much larger SSB is than SSE. So there was a lot of variation from the golfers. And if you look at the SSE from the completely randomized design output, you get 88,184. And these all add together. Okay. Now, what if we analyze the data again as a completely randomized design, but now with the block-adjusted version of the data? That's what we were looking at with respect to the second set of plots. So now, with my AOV function, I'm going to put formula equal distance.adj tilde type. Again, don't need to put person in there because I'm analyzing it as a completely randomized design, and I've essentially already taken out that information per person or per golfer. And look at the output that we get here. 8.48 for my F value, a very small p-value as well. Now, some of these components are exactly the same as what they were before. Others are not, because unfortunately some of the degrees of freedom aren't quite right, because we're not taking into account the true number of observations that we have because of how we're working with the data here. But the key is that what we're getting is similar results to what we did with analyzing the data correctly within RCB. Okay, so this takes us to page 20. Similar to what we saw with a completely randomized design, there is an underlying statistical model that's at work here. And so what we're basically saying is that how our actual response values come about, how our golf ball distances come about, can be represented by this statistical linear model, where we have one overall mean. You can say the overall mean value for all golfers plus the effect that would occur due to the golf ball type, plus the overall, let's say, ability of a particular golfer, plus a random error term. That accounts for that. There's going to still be some things that we cannot account for in our particular model, such as what was the wind speed for a particular day that something is that a golfer is playing, or maybe there's rain, for example. And so by using an RCB, what we're saying is that how our responses are coming about is through this particular model. Now, once we reject the null hypothesis of equality of means for the treatments, we want to figure out, well, which pair of means are unequal. And so once again, we do multiple comparisons. So this takes us to page 21 in the notes. And what we can do is use the same kinds of multiple comparisons as we did before, except for we have some adjustments with respect to the degrees of freedom. And of course, our MSE is going to be different as well, because the SSE is different. And so because of that, we can jump right into then looking at this with respect to the golf balls example. So let's say if we use Tukey's HSD, and I want to set an overall experiment-wise error rate of 0.05. How can I do this? Well, I use the exact same function as before, Tukey HSD. Here's my information from AOV saved in the object called mod.fit. My confidence level is 0.95. And then also I need to include an additional argument. Because we had type and person in the way that we wrote out our model statement in AOV, I need to say, well, which of those two things do I want to do this for? I want to do it for golf ball type. And here we go. So these p-values here have been adjusted to account for the experiment-wise error rate. And what we can see is we compare 0.05 to each of these p-values. We have that p-value that's less than 0.05, and that's about it, although we do have at least one that's a little bit close. So then, what that basically means for us then is that only for the max fly and Titleist B mean comparison, Is there sufficient evidence to actually say that indeed there is a difference in the mean distance of the golf ball types? Let's compare that to our plot. Remember how high max fly was in comparison to Titleist. That's why we came up with this. And then notice how, let's see, Titleist P and max fly. That was a p-value that was close to 0.05. So there's marginal evidence there of a difference. And here's Titleist P here. And we can see again how max fly is, again, somewhat shifted. At least part of it is shifted above. Definitely the median is higher for max fly than Titleist P. But also we can see that it's still not as clear cut, or I should say necessarily clear cut, but it's not as extreme of what we see here when we compare max fly to Titleist B. Okay. So what we can do then here, let's see here. So we need to figure out, well, how do we order these particular types of golf balls so that we can do our little graphic that helps demonstrate where the differences amongst the means are. And so what one could do is use the aggregate function with the adjusted distances. And what we can see is max fly has the highest value. Titleist B has the smallest value. And you can see what the second smallest, third smallest is, and so on. And using that as an ordering, as I did here, then we can draw our lines. So remember, we only found that max fly and Titleist B had different means. So because of that, that's why we had these two lines that go across on our plot. Okay. Now also, by looking at these adjusted means, we also know then, of course, that max fly is then actually greater than Titleist B. And so, what are our conclusions? Max fly and Titleist B are different with respect to their means because the confidence interval is positive for max fly versus Titleist B. Let's actually go back up here. There's that confidence interval. I'm always taking max fly minus Titleist B. So since the interval is positive, it means max fly is greater than Titleist B. Using this interval there, that's why you know max fly is greater than Titleist B, or you could just simply look at these adjusted means. Sorry, I kind of jumped around there. And so if I had a choice between those two, there's no question I would take max fly. Also, we've also talked about some other low p-values, so we have some marginal evidence there. And make sure, and we've already done this, compared to those box and dot plots. Okay, well, what about these other multiple comparison procedures? Can we use those as well with an RCB? And the answer is yes, we can. But we cannot use that pairwise.t.test function anymore, unfortunately. So instead, what we're going to do is go back to this package that we looked at a little bit previously, called this Agricola. And so again, this package is not installed by default in R. You're going to need to download and install it yourself. I need to tell R, first of all, that I want to use this particular package. Then I can use the Lsd.test function once again. I put my information from my AOV function in there. I tell the function, well, which part of mod.fit do I want to focus on? I want to focus on the golf ball type. I specify my alpha level. I don't need their little grouping output that comes about it. And if I want to do the Fisher's protected LSD, I put p.adj equal none for p-value adjustment none, and put a title with it. Okay, so what we get, if we can skip down here, here's the really important part. Here's my p-values. So max fly, Titleist B, I'm comparing it to 0.05. Wow, that p-value is really small. Max fly, Titleist P. Max fly, top flight. And even Titleist B versus Titleist P, it's kind of close. Titleist B and top flight, that's also close to 0.05. In fact, it's a little bit less. Only Titleist P and top flight do we not have evidence of a difference amongst the population means? So what does this mean in terms of our little plot? Let me see if I can get this all on one screen here. Hopefully this won't be too small on the video. So now we have, of course, then the same ordering as what we did before. And what we can see here is that Titleist P and top flight, we should have a line between them because the p-value is large. And indeed, that's what we do. Now for Titleist B and Titleist P, the p-value is a little bit above 0.05, but if we go with a strict 0.05 there, we would need also a line there. But then we don't have a line between any of the other ones. And so you can see how dramatic of a difference that is compared to what we had with Tukey's HSD. Okay, let me go back. To do the Bonferroni procedure, we use the exact same function, but now we say p.adj equal Bonferroni. Here's our p-values. Again, max fly and Titleist B. And in fact, that's the only one where there's sufficient evidence that the two population means are different. So in other words, this agrees with what we had with the Tukey HSD. Now, you could also do this as well with the MultComp package too. I give some guidance about how to do that in the corresponding program if you're interested, but you're not responsible for it. Okay. Now, just to conclude in this section, I want to mention that there are many, many other types of experimental designs out there. That's why there's a whole class at most universities on experimental design. And just to give you a flavor of what else is out there, we like with the wheat varieties example, we might want to include additional factors, not just the wheat varieties, but let's say fertilizer or was irrigation used. And so now we have, let's say, 3 factors. And so what this is like is what this is called is a multifactorial experiment. And you can do a completely randomized design with this. You can do an RCB with it. You can do other experimental designs with it as well. Another kind of experimental design is what's called a Latin square design. And what that allows you to do is to not just have one type of block, but actually 2 types of blocks. Then there also might be situations where, let's say, there's different sizes of experimental units for corresponding factors. So, and in this particular case, then, typically what these are called, there's other varieties, is what's called a split plot design. Again, this name comes from agriculture. So, for example, there may be physical constraints with respect to how different factors are applied to the experimental units, leading to different size experimental units. Also, there might be cases where, let's say, more than one measurement could occur on an experimental unit. So I remember when I was in grad school, the first time I saw this, we looked at a case from a study with respect to, I think they were trying to wash some kind of cloth. And after that cloth was washed, a measurement was taken here, 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 and here. So we had 5 measurements on the same cloth, and the actual treatment was applied to the whole cloth itself. Now, how to take into account this? That's what will be discussed in the experimental design class. This idea of taking multiple measurements on the exact same experimental unit is called subsampling. So anyway, so if you really like this stuff, I encourage you to take another class on experimental design.